Apologies for mathematics part of the audience. The outline will be, I'll introduce the main subject that I'll study in both talks, Young-Mills instantons on particular backgrounds. These particular backgrounds are significant, and we'll explore how they're related to, on the one hand, to brane configurations, to gauge theories and mirror symmetry in gauge theories, and to geometric Langlands for complex surfaces, and to very specific gauge theoretic solutions, which are useful in gauge theory itself, for example. Now, the way to organize a construction of such instantons is in terms of bows, and these bows are closely related to brane configurations again. And from this realization, you can see a lot of details that are important technical details, but also have very clear physical significance then. And they also allow to construct moduli spaces of bows. And so the main theorem in mathematics talk will be exactly that. Bow moduli spaces, which are quite tangible, which can be computed explicitly, they are isometric to moduli spaces of Young-Mills instantons that I'm about to describe. So please interrupt me at any point if there is any question. So Young-Mills instanton is a gauge field, or the connection one form, A, in a local representation, and it has a field strength, which can be explicitly computed from it, and then it is governed by a Young-Mills action. So action functional is basically L2 norm of the curvature. Oh, sorry, this is physics talk. This is F squared integrated over the space-time. So this star here is to account for the volume factor in the metric and the fact that each term of F is taken absolute value squared. So it's fairly straightforward to compute the extrema, the Euler-Lagrange equation for this. And these are Young-Mills equations. These are highly nonlinear, and it's an interesting sport to find solutions of these. And there are not so many solutions known, even though this is an extremely important equation in physics. So when we do quantum theory, instead of solving this classical equation of motion, we are rather interested in these types of integrals, where you have some expression in terms of curvature, well, in terms of gauge field or in terms of its field strength, and it's weighted by exponential of the action and integrated over all fields. Now, in Euclidean version of this is your integral, and this integral is dominated clearly by minima of this exponential factor of the action. In fact, for supersymmetric theories, very often, the whole integral can be expressed and localized in terms of these minima. So that's one of the reasons why this minima is important, and they're called instantons. And minimum of this is delivered by a field strength which is either self-dual or anti-self-dual. Now, why is that? This is an argument originally by Belavin-Polyakov-Schwartz-Tyupkin, and people call it Bogomolny trick. And it's simply based on the fact that if you take the difference of these two, or the sum of these two, F and F dual, so if you think of, instead of Young-Mills, if you think of Maxwell theory, then this expression is simply E minus B, electric field minus magnetic field. And if you compute its norm, it's this expression, the norm is greater or equal to 0. That's absolutely evident because it's norm, it's sum of squares. But at the same time, when you open up the brackets, when F meets F star, it becomes an action. And when F meets F, it becomes this term. And this term doesn't depend on metric at all. It is purely topological term. So as a result, you get an inequality, that your action is bound below by this purely topological expression, which is Chern character evaluated on M. But whatever its name is, it is a fixed topological quantity. It doesn't depend so much on the fields in the interior. And this minimum clearly is achieved only when the norm of this expression is 0, and that means that when this expression vanishes. So when the field is anti-self-dual, and clearly if you change the sign here to a minus, you get a very similar argument for self-dual connections. So self-dual connections or anti-self-dual connections saturate this bound and give minima of the action. Now, I'm interested in this interplay of gauge theory and gravity and gravitational background. So we would particularly be interested in backgrounds which are not flat, not R4, not T4, but actually have some curvature. And let's look at some simplest example. So as a warm-up, let's look at R4 in radial coordinates. So let's look at Euclidean R4. And the name for this space in the current argument will be A0 ALE space. So this is plain traditional, well, Euclidean metric on R4. R4 can be viewed as quaternionic line. And every quaternion you can write as pure imaginary quaternion times the exponential of, well, ij. This E1 is one of the quaternionic units. So they're often denoted by I, J, and K, 3 quaternions. And here I'll call them E1, E2, and E3. So E1 squared is -1, E2 squared is -1, and so forth. And E1 times E2 is E3. So if you like, this tau is the angular coordinate of 4-dimensional space. Right? So on a plane, you can have radial coordinates and write metric in these radial coordinates. Now, if you like, I can view R4 as 2 planes, and I can rotate them simultaneously in the opposite directions, and this angle of rotation is tau. Well, because we are in R4 in polar coordinates, instead of 1 radial coordinate, there will be 3 of them. And the way they appear is that if you look at this combination, Q, E1, Q bar, that is independent of tau, and it's pure imaginary. So you can write it in terms of T1, T2, and T3. These, if you wish, are your radial coordinates. They take values in R3. So what we've done, we've taken R4, and we now view it as a circle vibration over R3 parameterized by T1, T2, and T3, with a circle fiber parameterized by tau. Okay. You can take the flat metric, which is dq dq bar, and write it in these new coordinates, tau, T1, T2, T3. And it looks like this. At first, it looks like something singular is happening at the origin. But this is pure coordinate singularity, just as with a Euclidean metric written in radial coordinates in R2. It also appears to be something strange happening at 0, but that's purely coordinate problem. So this is just flat metric on R4 written in coordinates tau t. So here, there is this expression, 1 over t, which is harmonic everywhere outside 0. And omega is a form which is dual to that. So d of 1 over t is Hodge dual to d of omega. Or if you like, the curl of omega equals to divergence of 1 over t. That's what this equation means. So T is imaginary quaternion. It lives in R3. And tau parameterizes a circle. Tau is periodic. So tau equals to 4 pi plus tau. So if you look at this expression, tau is periodic with period 2 pi. So tau parameterizes a circle, and T parameterizes the base R3. Yes? This V will be 1 over 2t, yes. So if you modify this just a little bit, if you indeed call this V, and if you add a constant to it, which I'll call L, Then you get a new metric, and this metric is called Taub-NUT. So it is a slight deformation of R4. Let's see for a second what this deformation does to R4. Originally, if you look at the circle parameterized by tau, you can easily compute its perimeter. So it will be 2 pi divided by square root of this expression. So when t goes to infinity, for example, then this expression goes to 0, and the size of the circle, because it's in denominator, the size of the circle opens up. Right? So that's fairly intuitive. If you look at S3, sphere of fixed radius, what we've done here is we fibered it, we Hopf fibered it. In physics, it's called monopole bundle, for example. And what is happening is that the whole of S3 is increasing proportional to the radius. It's scaled with the radius. If instead we look at this v, as t goes to infinity, this v tends to a constant. So in this case, the circle tends to a constant radius. So what's happening is the base S2 is still increasing, it's inflating, but the fiber tends to a constant radius. It's sort of a squashed sphere. There's also something interesting happening at the origin. When you approach the origin, this tends to infinity, so the circle actually shrinks. So let's consider the origin in R3 and pick a line. If you stand at the generic point in R3, then over that line there is a circle parameterized by tau. As I mentioned, if you go to infinity, the size of that circle stabilizes. But if you approach the origin, v goes to infinity, so 1 over square root of v goes to 0, and the size of that circle shrinks to 0. So as a result, you get this sort of cigar shape, and that's for a single Taub-NUT space. If you compare this to R4, this cigar shape in terms of that R4 is what used to be a complex plane. It's the same complex plane, except now the circle, as you increase R, does not tend to infinity, but actually tends to a constant. Right? That's what will happen to a plane if you change the metric so that a circle at radius R tends to a constant perimeter. Now there's another modification of this, which is called multi-Taub-NUT space, where instead you have a bunch of such points. So all you do is you keep the same expression for the metric, but in V you have a constant L plus sum over such contributions, each centered at particular nu1, nu2, nu3, and so forth. And this metric was found by Gibbons and Hawking. And it was found by looking for minima of Einstein-Hilbert action. So these are gravitational instantons. They also were significant in this Euclidean version of quantum gravity. These days they are significant because, in my view, this is the simplest example of a Calabi-Yau space. So in physics terms, it's important because it respects half of supersymmetry, which in other words means that it has 2 covariantly constant spinors. Or in other words, all these statements are equivalent. It is a hyper-Kelly space. So what we would want to study are instantons on these spaces. What this is a complex manifold. It is a blow-up of a k-1 singularity. It's a twofold. This is ALF. As a complex manifold, ALF is indistinguishable from ALE. It's only the metric which distinguishes the two. So Taub-NUT as a complex manifold is C squared. It's only the metric which changes. But complex structure doesn't know about the size of the circle. It means that if you look at spin bundle, then the number of covariantly constant spinors is half of the dimension of the spin bundle. Yeah, as I mentioned, it's 3 statements in this case of a twofold equivalent. Right, so now the significance. Why study instantons on Taub-NUT? Well, we'll discuss it quite a bit today. Yes? Exactly, it is SU2 holonet. So as we'll discuss quite a bit today, it directly, so each instanton on Taub-NUT corresponds to a particular Chalmers-Hanany-Witten brane configuration. Well, that is sort of string theory point of view, but that allows us to approach the gauge theoretic point of view. Each such instanton on Taub-NUT will correspond to a vacuum of quantum gauge theory in, well, now this is the difference I would like to emphasize. So either 3-dimensional gauge theory with n equal 4 supersymmetry, or 4-dimensional with n equal 2 with impurity walls. And I would like to emphasize this difference because the second view allows us to make exact statement of gauge theory mirror symmetry, which takes one such theory to another such theory, but the moduli space of it is unchanged. So in this case, the gauge theory mirror symmetry actually acts as an isometry. There's no change at all in the moduli space of vacua, except some branches are interchanged to change the labels. But metrically, they are the same. Now, it also relates to geometric Langlands for complex surfaces and various interesting M-theory compactifications with backgrounds which themselves induce various M brane charges. So there is interest in the play between geometry and the rest of M-theory, if you wish. And also, mathematically, it leads to natural generalization of quivers. So bows that I'll talk about today is just the first step in these generalizations. They're followed by what I'll call slings and monowalls. And it's an interesting trajectory to follow purely mathematically. I am confident that each of these objects has its own significance in representation theory, for example. So let's play this game. We'll realize instantons as codimension, relative codimension for D branes. So you can take a dp brane inside of dp plus 4 brane, and that will be our model for instantons, and you can wrap it on the manifold you're interested in. Now, if your manifold has some isometries, if it has some symmetry, continuous symmetry, you can t-dualize along that symmetry. As a result, you'll get a different realization, some different dp plus k brane, intersecting some other brane inside of a different manifold. And one can get quite a bit of mileage by analyzing this for different p's. So surprisingly, if you change the value of p, you'll get very different physical interpretation of this. So let's play this game with different values of p. So we'll start with D2 brane inside of a D6 brane. So if you simply look at such configuration, then as found by Douglas and Douglas-Moore, by analyzing this D2 brane walled volume, you recover Atiyah, Greenfield, Hitchin, and Mahan construction of instantons, and the whole story unfolds. Now we would like to have our instantons on Taub-NUT space. So we look at 2A string theory in this 10-dimensional world, where 4 of the 10 dimensions are Taub-NUT, and the rest is flat. So D6 is entirely wrapping Taub-NUT, while D2 appears as a point on Taub-NUT. So in this diagram, this crosses signify the directions in which D6 brane stretches. Now, Taub-NUT, as I mentioned, has an isometry, the rotations around the circle fiber. So we can t-dualize along that direction. Now, in this game, again, if you t-dualize direction perpendicular to a D brane, then it gains that direction. So D2 brane becomes D3, wrapping the 6 directions, the circle. And if you t-dualize along the direction containing the D brane, then you lose that direction. So the D6 brane becomes D5. Now, interestingly, when you T-dualize Taub-NUT, you end up with an S5 brane in the directions orthogonal to Taub-NUT. So if you visualize this in a picture, if this direction, the periodic direction, is 6, then we have D5 branes, which are localized at points along the 6th direction and stretch along direction 7, 8, 9, which here are, sorry, D5s are stretching along 3, 4, 5. So vertical directions here are 3, 4, and 5. Similarly, NS5s are localized at some other points, which are labeled P, and stretch in other directions, 7, 8, 9, in this direction. And then 3 branes actually wrap this. So that is Chalmers, Hanany, and Witten configuration. And in fact, it's this brane configuration, which in this case is sort of an analog of Hitchin spectral curve if you were dealing with, let's say, doubly periodic instantons. So if you study doubly periodic instantons, you end up by T-dualities with a Hitchin system, and that has spectral curve in between. So if you like, this is sort of spectral data for that instanton. And we'll discuss first appearance of a gauge theory. So if you look at the volume of D3 brane, that is described by, well, actually maximally supersymmetric gauge theory. But that theory has some defects which account for presence of these branes, which we'll discuss. They break supersymmetry to n equal 2. And one can analyze this theory and its vacua. And analyzing this vacua leads us directly to this notion of a bow. There's another realization of this. One can view this from the point of view of M theory. So if you lift this to M theory without any branes, well, that will be M theory again on 11-dimensional space with a Taub-NUT with an extra circle. So M theory circle is this 10th direction. Now, lifting the 6 branes to M theory turns brane into pure background. It becomes Taub-NUT in these 3 directions and extra circle. So if you like defect of this vibration, that circle which we are forgetting is D6. And D2 is M2. Right, I will not apologize every time. I sort of apologize for this being physics talks in the beginning, and tomorrow's talk is math talk. It will be very different in flavor. But again, if there's any question, just ask. So what's interesting to me about this configuration is, first, when you look at it, it looks like this is Calabi-Yau, this is Calabi-Yau. You take their product, it looks like you have a good M theory compactification. Well, apparently not. This is not a solution of M theory. And it has to do with the fact that the M theory action contains this term, R to the 4th times a wedge 3 form. So Taub-NUT itself has non-trivial R squared. If you integrate R squared over Taub-NUT, you get 1/12. So as a result, this R to the 4th is a source in your Einstein equation for C3. So if you look at this purely gravitational background, it gives rise to a C3 field, and that can be interpreted as fractional M2. So one can play an interesting game of how, for example, Hanany-Witten effect in this story, when you carry NS5 across D5, a fractional D3 appears, how that manifests itself in terms of M theory. And we sorted that story with Rubin Minasan. But an interesting open question is actually finding an M theory background that is consistent. Yes? Yes. Because that C3 is a non-constant field. It will have dC3, and that will back react and change this. So, no. It will actually change Taub-NUT cross Taub-NUT background. So it back reacts on the same. So something is happening in this core. So it's an open question, finding a consistent solution here. But that solution will have this interplay of the metric and C3. And I think it's a tangible problem because it has large amount of supersymmetry. Right, so yes, that will resolve all problems. Yes, that's right. That's why it is so interesting. Yes. And it has the same amount of supersymmetry you expect. So you can actually find the spinors, and it's very constraining. So it's a doable problem, finding this background. All right, so what do we learn from this brane configuration? Well, if you look at the world volume of D3, if not for these other branes present, that would be maximally supersymmetric Yang-Mills. But then these branes, as we'll argue in a little bit, present some defects in this Yang-Mill, some walls, codimension 1 walls, where something is happening. If you apply string theory as duality, then that duality simply interchanges D5s and NS5s. You'll end up with a different configuration like this, which is again the same UN super Yang-Mills with other types of defects. Because as duality takes one configuration into another, you expect that it takes vacuum of one to vacuum of another. So what it means is that Coulomb branch of this first theory, of M theory, given by, well, that's one branch, becomes a Higgs branch of the other theory, of W theory, and Higgs becomes Coulomb branch. But the main point is that they are entirely isometric. They're not the same complex varieties, but they're actually the same differential manifolds. They have exactly the same metrics. This gauge theory mirror symmetry is often stated for three-dimensional theories and not four-dimensional theories, in which case the statement is that this Coulomb branch is the same complex variety as the Higgs branch, but they have entirely different metrics. If you like, one is Taub-NUT and the other one is R4, or analogous statements in high dimensions. But in this case, it's exact isometry. Right? So again, in 3 dimensions, gauge theory mirror symmetry is not an isometry. It changes modular spaces. Before we explore what sort of defects we have here, let's try a different case. Let's put p equal to 0. So now we have 0 brane inside of a D4 brane wrapped on a Taub-NUT, and play this game with dualities. Well, we already know how to T-dualize 6 direction. That gives us NS5, D3, and D1. You can as-dualize that if you like. Or you can lift it to M theory. When you lift it to M theory, you'll end up with Taub-NUT. D4 lifts to M5, which wraps M theory circle. And D0 is some sort of Kaluza-Klein mode of the metric. But now what we gained is that in M theory, we have these 2 circles. So we can play a game. We can reduce, in the first case, we call this circle circle of M theory and got this configuration. But now we can choose a different circle of M theory and have this configuration. So if you choose 6 circle, then Taub-NUT, as we already discussed, manifests itself as D6, K D6s. M5, since it was wrapping the 6th direction, becomes D4. And this Kaluza-Klein mode becomes the fundamental string. Right, so this configuration was explored by Digraph, Holland, Sulkovsky, and Waffa. And then Menchuang Tang and Ed Witten used it to actually relate modular spaces of these instantons to WZW. We'll mention this in a second. And of course, one can complete the circle, and again, one can reinterpret, well, one can choose one's favorite picture to talk about, but it's these 2 that I want to focus on. So the exact statement here is that if you focus on these 2 shared directions, then you have 2-dimensional theory living on the intersection of D6 and D4 branes. Right? So as these authors argued, that's described by holomorphic WZW on the intersection. At the same time, when you look at the shared directions, you have this one-dimensional theory here, and sort of think in physical terms. You have the system which has 4 directions, where you have this gauge theory living, and one shared direction. So if you like, if you view this as your fast directions and slow directions, the usual quantum mechanical problem, then solutions here are given by instantons on Taub-NUT, minima. And then, as a result, you get one-dimensional quantum mechanical problem on the moduli space of instantons. So the configuration space, or if you like the Hilbert space here, is the L2 cohomology, or if you like the harmonic spinors, on the moduli space of instantons. So again, because of this correspondence, you get this claim that L2 cohomology of instanton moduli spaces, summed over all charges, carries the representation of some gauge group. Well, it corresponds exactly to WZW weighted, so to the highest weight representations of corresponding current algebra. And the reason it is, well, manifestation of Langland's duality is that if gauge group here was G, then gauge group here is Langland's dual. So in this paper by Menchuang, you can find the exact expressions. Well, looking at this side, you can simply write the generating functions, product of ratio of theta functions to eta functions, generating functions for these dimensions, and as a result, it predictions for dimensions of L2 cohomology of the space. It's a beautiful formula, and it's really hard to reproduce. It's very hard to compute to this L2 cohomology. So it's very nice correspondence and gives you powerful prediction here. And people are working now really hard in trying to compute it on this side. There's a lot of geometry and analysis involved in it. And then there is P=1 case, which, as far as I know, is unexplored. I want to mention it because that's an opportunity. I think we know much more about M5 brane now to attack it. So if you now have D1 brane inside of D5, wrapping Taub-NUT, you T-dualize the only compact direction we have now, and that becomes configuration of NS5s, D4, D2, lifted to M theory, and now almost everything is gone. You only have 2 M5 branes intersecting and D2 brane connecting them. So an open question which is there to explore is, well, is there some physical depth here? Is there a different description of this brane configuration where we can use our knowledge on this side to learn something about M2, M5, or make some new mathematical claim? So now that we ran through all these dualities, let's get back to our focus and analyze this configuration. Yes? Well, they don't intersect, they're sort of transverse to each other, like this. They share 2 dimensions, and then 4 and 4. So 4 dimensions. 4 dimensions horizontal, 4 dimensions vertical, and there can be some M2 stretching between them. All right, so we would like to have the view of this gauge theory. We already know that in the world volume of D3, well, yes. Left or right? One transverse circle. In each case, it has only one transverse circle. Yes. On a single. By decoupled, you mean NS5 decouples from its own images, from the bulk? On NS5, no, I do not know. I understand. I understand. Right. So that's right. It has its own images to take care of. Yes. Right. So well, there's two games to play. So one game is the configuration we're interested in is string theory configuration. So the size of one of the circles, 10 or 6, can be as small as you wish. It's not the limit that you would want. The limit that you mentioned before is when you make it large. But in that limit, you might have some effective description of it. So what I'm arguing is that here we know exactly how to describe this configuration. So we have something, some statements about that, that every configuration here is described by a bow, which I'm going to describe. So we have some answer. Now, is it a different way of formulating it using fields on M5s? That's right. That's right. They're problematic if you want purely walled volume theory. Yes, that's right. Right. However, last row gives us some answer to that.
So I'd expect it would suffer from the same problem.
Right. So in a way, the purpose of this is to state a question. Right. So on the walled volume of any D brane, as discovered by Witten, is some Young-Mills. So just pure D brane, there will be maximally supersymmetric Young-Mills. Now we want to understand what this presence of other branes means. Analyzing this whole configuration is a little difficult because, well, it's relatively non-local. There will be Ramon-Ramon charges, Schwartz charges, and studying it together is hard. So instead, let's study one at a time. So if you study D3, D5 intersection with D3 ending on D5, instead of analyzing the intersection, let's move it a little. So first you can move D3s so that they coincide. Once they coincide, you can move them off a D5. Now, it's fairly clear that there are massive strings connecting two D branes. The mass is proportional to this distance. And that because that string has a single end on D3, it is transforming in the fundamental representation of the group on D3, of the gauge group. So there is some fundamental defect at that point. And you can see what's happening when you move back. When you move this brane back, the mass of that fundamental hypermultiplet vanishes. So you have massless fundamental hypermultiplet. And then moving the branes apart corresponds to giving it some expectation value. Well, so we have massless fundamental hypermultiplet, Q with some expectation value of Q dagger or some quadratic expression in Q. Now, what about this cross D3 and S5? Well, we can play a similar game. We can move it and then split it. When you split it, you have one gauge group here and a different gauge group there on two D3 branes. And now we have bifundamental string connecting them. It transforms under this gauge group and under that gauge group. So you have massive bifundamental. If you move back, it becomes massless. And if you move here, it gets expectation value. So we want to argue that now we have maximally supersymmetric Young-Mills in 4 dimensions, where one of these 4 dimensions is a circle. And in that dimension, there are walls of codimension 1. These walls introduce fundamental hypermultiplet And these walls, they cut your space in two. There's one gauge theory on one end and one gauge theory on another, and there is a bifundamental hypermultiplet connecting them. So let's represent it this way. We have a circle. We have lambda points, which are positions of D5s. We have p points, which are positions of NS5. Whenever you have a p point, it cuts your circle. So if a single p point is there, then a circle is an interval. And then, when it cuts it, it introduces a bifundamental hypermultiplet there. So it transforms as fundamental of this gauge group and anti-fundamental of that. And at a lambda point, you have a fundamental multiplet. You have some auxiliary space and a map from this point, from the phi by this point to phi by that point. So I hope it's evident why I call this bow. So let's see what these bows are useful for. For example, let's find some bow moduli space. Let's say we have only D3 brane and NS5 brane. What's the moduli space of that? If you like, in terms of instantons, we are studying, however funny it sounds, we are studying one U0 instanton on Taub-NUT. Well, in terms of gauge theory, we're studying gauge theory on a circle with one bifundamental defect. Well, it is a U1 gauge theory, so it will have this 3 Higgs fields, and we'll have a connection in that direction. Now, if you're in the bulk, you can impose your D and F flatness conditions, or in mathematical language, you look at hyperkähler moment maps under the gauge group transformations. And these are given by the NUM equations. So the derivative of T1 is commutator of T2, T3, and derivative of T2 is commutator of the other two, and so forth. And because they're all U1, they commute with each other. So the derivative of each T is 0. Well, that means that you have 3 T's which are constant. So T1, T2, T3 gives you a point in R3. If you look at a connection on an interval, well, up to gauge transformations, they're all the same, except if you look at gauge transformations which act as identity on left and right, then there is a leftover. There is a monodromy from one end to the other. So if you like, you can gauge your T0 to be constant. Moreover, it's constant up to a period up to 2 pi, so it's a point in S1. Like it's just gauge, relative gauge transformation between point at 0, phi by at 0 and phi by at L. 0 to L. It will come out in just 1 second. So far, we only look at gauge transformations in the bulk, which don't do anything to the ends. And then we'll look at what D flatness conditions for those points. So far, D and F flatness conditions in the bulk here tell us that you have 3 T's which are constant and another T0 which is determined up to 2 pi. So the space in the interior is R3 cross S1. Now let's look at what happens, what are the conditions imposed by gauge transformations at the endpoint. Well, at the endpoint, D flatness condition, now this gauge group acts both, it acts on T's, it shifts T0, and it acts on Q, on this bifundamental. So the D flatness condition for that, if you like the moment map acting on Q, is this. I should have written this as Q bar, E3Q. And acting on T's, it's this combination, essentially T itself. So when it vanishes or when it equals to constant, we get this condition. So if you like, what we end up with is a 4-dimensional space parameterized by Q's, R4 or H if you like, and then R3 cross S1 parameterized by T's, and we are dividing by remaining U1 acting at the endpoint. Well, the metric on this original space is just metric on R3 cross S1 It came from, well, squaring each of these and integrating from 0 to L. So this is the metric. Metric on R4, we already discussed. In this radial coordinates, it's written this way. If this is my R, you can see why these radial coordinates were useful in the first place, because they are exactly the expressions appearing in the D-flatness conditions. So that's what's written here is simply metric on flat metric on this space. Right? T's are here, R and theta are here. There is remaining U1 action on this, which shifts T and theta at the same time. So we want to divide by that. Right, so we have this flat metric, and we are dividing by this U1 action. Now, invariant of this U1 action is this difference. So you can clearly, well, you can just complete the square, writing some metric in terms of tau, and the little piece, which is in terms of either T0 or theta, doesn't matter. And then we want to divide by the gauge group. This theta can be moved up or down any way you wish. So what do we have? We have a level set, which is 5-dimensional space parameterized by this T's and tau and T0. And we have gauge group action. We have these orbits of the gauge group action, and we want to divide by that. So the quotient is the moduli space of the bow, or if you like, it's a vacuum, moduli space of vacuum of that theory. And the metric on that comes from this metric, but if you look at tangent vector here, you should, when you lift it, you should look at tangent vector orthogonal to the fiber. The fiber is parameterized by T0, so essentially you simply have to cross out the term which contains T0. Right? You look at part of the metric which is orthogonal to dt0. And that, as you probably recognize, is exactly the Taub-NUT metric. So moduli space of this bow is the Taub-NUT itself. We also get a little bit extra information. Whenever you perform Hyperkähler quotient to look about moduli space of a gauge theory, that space carries some extra data on it. That space was space of gauge orbits. So as a result, it carries a principal bundle over it. There was a metric up there, so there was a connection on it. That piece is exactly that connection. And that connection is itself anti-self dual. So it's an abelian instanton. Taub-NUT space carries an abelian instanton. That will be important for us. Now, this was an example of computing bow moduli space, and this can be done quite explicitly when the rank is 1 or 2. When it's higher, it becomes a little harder. So, but I'm addicted, when I'm faced with some space, I really want to know its metric. If it's differential manifold, I want the metric on it. So how can we actually compute those metrics in general? Now there's a pretty neat picture which comes out. That is a story that we started with Roger Bilavsky. So there is an integrable system associated with each bow. Also, every bow, if you look at UN instantons on AK ALF space, then the bow combines two Dynkin diagrams, one associated to the gauge group and the other associated to the underlying space. Now, today, for simplicity, I'm talking only about UN instantons on Taub-NUT, but you can look at any G instantons on any ALF space, and in that case, too, the story will combine two Dynkin diagrams, one associated with the gauge group, the other with the underlying space. So in our story, as I was describing, there's a circle, and there are lambda points which are positions of D5 branes, and P points which are positions of NS5 branes. In the interior of each interval, and I'll describe this in much more rigor and detail tomorrow, there is a system solving norm equations. So in each interval between lambda points, you have T's which satisfy this equation. Now this equation is integrable, as discovered by Nam, and the Lax pair is given here. There is some auxiliary parameter here, zeta, and then this L and M combination satisfy this system. So this is a Lax pair for the system of equations. If you open it up and look at each power of zeta, then you recover these three equations. So whenever you have a Lax pair like this, you know that eigenvalues of L do not depend on S. So that gives you a spectral curve. Right, so if you look at eigenvalues of L as functions of zeta, then you end up with a spectral curve. This L was quadratic in zeta, so the spectral curve is secretly living in tangent bundle to P1. That's sort of a sketch of the spectral curve. It lives in TP1. And it is a cover of the base P1, and it covers it as many times as the rank of this Nam system. Now, as I mentioned, if you forget about lambda points, you'll get these P points, and that will be your, well, that's associated with the Dynkin diagram corresponding to the underlying space. And if you forget about lambda points, that will be the Dynkin diagram associated with the gauge group. So that's how the bow combines the two. Now, I'm emphasizing this combination of two because our final result will apply to any gauge group and any type of underlying space. I want to say any. Well, is it a theorem? So clearly there are instantons and all these other gauge groups. So what you mean is we don't know ADHM construction for that. Now, what I'm arguing for is that bow separate different pieces of ADHM construction, and generalizing the story for bows, in my view, is easier than generalizing the original ADHM. So bows give you some insight here. So I want to. So it's true. There's no theorem either way now, but I'm working on it now. So for classical, well, we can discuss other groups. So it is important what is happening at these special points, P points and lambda points. So at a P point, as we argued, the P point is position of NS5, so it really separates this into two intervals. Each has its own gauge group. And there is a bifundamental map from one side to another. That's B left right and B right left. So there's two maps. And the conditions that we already used before, the D and F flatness conditions or moment maps at the left or the right limit points, are these: that limit of L, one of these Lax pair matrices, is a product of these two expressions in terms of B. And this nu here is simply the level of the moment map, or if you look for Eliopoulos parameters appearing in D-flatness conditions. So every P point has its own parameters, which you choose the way you want. And then it relates L to product of B's. If you come from the other side to the same P point, then limit of L from that side is the product of same expressions, but in the opposite order. Okay. So the statement is that the spectral curve that we had was a curve of eigenvalues of L. Right? And if your matrix is written as AB, then eigenvalues of AB are the same as eigenvalues of BA. So as a result, as you cross a P point, spectral curve does not change. So if you look at this circle, for each interval between lambda points, there is one spectral curve. What's the significance of these P points? Every P point had a particular level And that level defines a section of TP1. That's what these yellow curves mean. Right? So there are different curves all living in the same TP1, and there are various sections which are singled out. So if you look at these curves, so for each interval between two lambdas, I draw a point here. So this interval corresponds to this point, this interval corresponds to that point, this interval corresponds to that point. So that is a Dynkin diagram of the gauge group, a fine Dynkin diagram of the gauge group. Each vertex of the diagram carries a spectral curve. Whenever there is a p-point on corresponding interval, then in addition, there is a particular section of P1 given by the moment map level. So again, I'd like to emphasize what's happening here. Now, each vertex of Dynkin diagram corresponding to a group carries a spectral curve. All these curves live in the same TP1. P-points assign a P1 curves, or sections of TP1, to some of these vertices. These P-points have to do with Dynkin diagram of the underlying space, not of the group. When you have connected vertices, then these two respective curves intersect, and you actually mark their divisor. The divisor has significance. So intersection of this green curve and this red curve is significant, but the intersection of this green curve and that green curve is not. You view them, even though they lie in the same space, you don't about the intersection. And then a curve at a vertex intersection with a moment P1 is also marked. So if these two are sitting at the same point, then you mark that divisor as well. So one can view all this as a single multi-component curve, but some of these intersections are counted, they're actually a single point, and some are not. You actually have to, well, resolve it if you like. Then we derived with Roger Bielowski the Keller potential on the moduli space. So first let's parameterize the moduli space. Every curve can be written this way. So in TP1, we parameterize base P1 Riemann sphere by zeta. And eta is natural coordinate in the fiber, so that eta dd zeta is the natural tangent field. So then any curve on the ith interval of, if the data is of rank R1, can be written this way as polynomial degree R in eta. And coefficients are polynomials in zeta. So if you like, our parameters are the coefficients of those polynomials. Well, that's too many parameters. They'll be fixed in a second. Then we form a Legendre potential. So we write a very specific function for these. In fact, this complicated function can be written fairly succinctly as a single integral of the contours of this combined curve that I mentioned before. So let me now single out what are the terms here. So first, there are curves for each interval. Some of them we consider intersecting and some not. And then there are P1 sections associated to each P point. So if you are sitting at some vertex, then there are terms corresponding to that curve, to the red curve, for example. And when that vertex is connected to another vertices, then you also look at the difference of values of eta for red curve and green curve, for example, constructing this term. If your curve sits at the same vertex as a section of P1, then you also view that as part of your curve and look at those differences. So if you like, you can view this whole thing as one curve, and you look at its basis of pi1, of its cycles, its symplectic basis, look at half of it, and then write this integral. So then you perform Legendre transform for this f. Legendre transform with respect to these interior coefficients is put to 0, so df, dw is all 0. These are constraints for our spectral curves. Well, these are so-called triviality constraints, and to be honest, this is the most non-trivial part of the game. The transcendental constraints involving the Billian integrals. And then derivative with respect to v's, these coefficients are called u's, and the Kähler potential is in terms of z and v, z and u, I'm sorry. And that's the Legendre transform in z and v. So this is a generalized Legendre transform construction of Hitchin, Karlhede, Lindström, and Wojcik. So the generalized Legendre transform is this prescription of going from f to Kähler potential to get hyperkählemetric. So in this case, it simply emerges from the bow and analyzing underlying integrable system. So let's run physically through what we covered today. We have various brane realizations of instantons on Taub-NUT. And in each case, it's fairly straightforward to follow the rules and see various dual configurations. Today we focused on only one of these, namely Chalmers Hanany-Witten configuration. And from that, we recover the bow. From the bow, you can get moduli spaces. You can do it explicitly if the ranks are not too high. In principle, you can get Kähler potential by this prescription, if you like. You can also compute the instanton itself. So as an example, I computed one instanton on Taub-NUT space. Computing one instanton on multi-Taub-NUT space is not much harder. And with Chris Blair, we used it to construct one singular monopole with arbitrary number of singularities. The expression in that case comes out to be surprisingly compact and simple. And that is done using a bow where the ranks are either 0 or 1. So probably the simplest bow to work with, but it gives this non-trivial solution. Right, so today I hope I convinced you that bows are useful for getting new solutions or for exploring some physics. And there is a lot still to be explored here. I mentioned some of these configurations to which it relates to. And I hope it will stimulate some discussion. I'll stop here.
We have quite a lot of time for questions, so I hope people have a lot of questions. Okay, so then maybe I'll ask. So the potential that you wrote here, that's for UK instantons on a AALF space that's of type A N or something?
Well, I would want to conjecture that this expression is general for any G instanton on H type of space. What is important about this G and H is the interplay about which spectral curves feel each other and which don't. So for example, this cycle appears only between two curves which are connected by an edge in our story. In other words, whenever the 2 points are connected by some root, when there's a root to go from one to another, then this cycle appears. If not, then not. So that's the only information from... Well, so if you want to abstract to general gauge group, then you only talk about weights. So there are weights which are connected by a root and weights which are not. So if it's not connected by a root, then you view these curves as not intersecting. If there's a root connecting two weights, then you do have this cycle. And I conjecture that for G instanton on H type of space, you still have this expression. And the only information about G and H is about what spectral curves are and how they interact with each other. So with Jacques Hurtubise now we're trying to algebra geometric approach to construct this to see how this works for classical groups for SO and SP. And in the process, there's nothing that stops one from using the same approach for any gauge group G for multi-Taub-NUT. So the next step would be recovering the story for D-type ALF space and then combining the two. So at the moment, I don't see in principle anything which stops us from talking about G2 instantons on D-type Taub-NUT, for example. Right. Well, right. Well, brane interpretations take us only so far. But once we have, that's why I was trying to put it in some form which doesn't care about realization, and it allows generalizations. Well, there are big puzzles there. So. Gadde and Witten asked this general question about what are the possible boundary conditions for super young mills. And they classified lots of them, but if I look at SO instant D-type ALF, then I'm interested in orientifold configuration, which is not in that classification. So it's an open problem how to describe it. And this algebra geometric construction that we're working on with Jacques Courtubis answers this question. The mathematical side of this question. So what is happening is that you have a bunch of NS5 branes which are positioned exactly at the same orientifold point. And describing that is not so trivial.
Okay, if not, we'll thank the speaker again.